Hi there, guys. My name is Jamie Gilchrist, and I'm here today to present a collaborative piece of work between Napier University and Lasting Asset, who are a university spin out from Edinburgh who work in the fraud space. So I'm actually filling in for Professor Bill Buchanan today, who was unable to make this. So I've kind of sort of prepared things as best as I can. I'm a software engineer and systems engineer, so I might be light on certain parts of the cryptography, but happy to sort of answer any questions later. And certainly, a lot of the core information is in the paper. But hopefully I can kind of talk us through this and add some value to that. So, um, just to kind of set the context here. So the aim of this talk is for us to show how fully homomorphic encryption, or indeed partial homomorphic encryption, can be used in fraud analysis, and particularly for our case, is the idea of a blacklist and whitelist for IP addresses. Um, and so if you consider, devices like firewalls or even a provider themselves, they might have this concept to the whitelist in which an IP address or a IP within a range is on the whitelist and therefore is allowed to do something, some kind of logic that they're allowed to do, or they could be on a blacklist due to being, an IP address that's being linked with nefarious activities, and therefore the kind of idea is that there's these two sort of sides to that. And what I'll do is I'll go on to talk about how that's kind of tackled now and maybe some of the problems that are associated with that. But I just kind of set in that scene, which is, we want a way that clients can check if a particular IP address is on a whitelist or a blacklist. But we want to do that in a privacy preserving way, in a way that doesn't compromise either the blacklist or the IP address that the client wants to check. And just to kind of sort of set it again, this is not necessarily the client's IP. This might be an IP address that they've sort of observed in their system, and they just want to check, globally or over a bigger set of uh, typical companies in their industry, for example, has this IP address been seen there as well? So that's the context. Obviously working within privacy aware fraud. Um, and so when we look at these whitelists and blacklists, there's kind of two ways to handle that. When we look at an IP address itself, it's considered as a an artifact that's considered PII, so therefore it's personally identifiable information and then covered by standards like GDPR and the US CCPA for the California Consumer Protection Act. And so even the act of sharing an IP address with a third party to check against a blacklist is actually something that does sort of open up a bit of risk in terms of breaching GDPR and kind of opening up extra risks there. So with that in mind, there's two ways to sort of handle it. And so I should mention as well that even a hash of an IP can be considered, and certainly is by most standards of the regulators, to be PII as well. So if we look at that problem and we say that we could basically have this blacklist, we could share the blacklist with the client. The client could then locally check their address that they want to check against the blacklist. But of course, in that scenario, we've opened up the blacklist to all the clients, and people can then analyze the blacklist and say, who's on that blacklist, and probably get some other kind of analysis out of that as well. Another version is that we just say the client, sends the IP address to the server or service, and then we would do the check, and then we can sort of report whether it's a hit or a miss, right? And in that situation, the concession is that we have to handle the personal information, the IP address. And of course, with traditional encryption, you could encrypt this at rest and you could encrypt it in transit. But what you can't do is encrypt it. Sorry, you can't process while it's actually encrypted. And in many ways, in computer processing, homomorphic encryption, and certainly, the later versions of this, so the fully homomorphic encryptions and things like the fourth generation, are almost like a holy grail in many ways for computer processing, especially with personal information, because because of that fact that you can abstract away and actually still do analysis on it while it's encrypted. So it kind of changes that paradigm of, you have to trust us because we say we do X, Y, and Z to handle your data. It's more like don't put the data in the hands in the first place, and kind of saves a lot of hassle. So that's the problem. That's kind of how it can be solved at the moment. And I just wanted to switch on to kind of to how we're using homomorphic encryption for this. So, pardon me, this formula here, what this is basically saying is that for this to be true, that we can take a message 1 and 2, which would be sort of these two messages to encrypt, and say for simplicity's sake, this is an integer 5 and 5. If we take those two and add them together, a clear text, and then encrypt the value, we should obviously have 10. And the kind of balance here is that we can also encrypt value 1 and then encrypt value 2, so the two messages individually, and then run an operation on them, and then we should get the same result when we get the results, which is also encrypted, right? And then once we decrypt that, that should match the same result that we have when we actually do it through clear text. So that's the kind of sort of one-liner of how homomorphic encryption actually is applied and how it kind of works. And so when we've got this symbol here, this is basically saying any operation. So I just, for example, used addition, but we could have a multiplier. And certainly for some of the partial homomorphic encryptions, they would use, scalar multiplication or addition, or maybe XOR bitwise operations. So so that sets the scene for that. Just kind of go into now, just look at how this looks in a system setting. So what we've got here, we've got a few flavors of the ways that this can be set up. But what we see here is basically us collecting various documents from different sources and different formats. Could be spreadsheets, can be complete documents, dumps of filings and things like that that are actually added to company's house. There's no kind of limit to where the sources are. And then we have these indexes of interest and attributes that we want to capture. So there might have been a certain number of pre-processing done in these documents. For example, the documents themselves can be lists of attributes from known fraud events, or the feature weights for things that are relating to active fraud that we might be monitoring. And when these attributes are stripped out, these can be added to a homomorphic blacklist, and or indeed a whitelist. And what's happening there is we basically isolate the different attributes, and then those themselves are encrypted, and they're stored in the blacklist. So now, if we look at the client here, which we can just say is Alice, this client wants to then, they want to check and see if a particular email address or a particular phone number or some other attribute is on the blacklist. They now just need to locally encrypt their data, and then what they do is they sort of compare the data against the whitelist or the blacklist, and it basically uses like a subtraction. So if you imagine you've got these two sort of encrypted values, if they cancel each other out and come to 0, that's telling you that it's an exact match, and therefore you could say that it's either on the whitelist or on the blacklist. And so in this setup, we're collecting this kind of data sort of tangentially from the client that's consuming the white and blacklist here, and that's just kind of one potential way, or indeed one of the ways that it is employed at the minute. The mention of Gen AI here is because we use that to to extract various pieces of information from sort of chunks of text. And in many ways, that can be behind the scenes actually doing code execution, where it'll run a script which is doing similar regex and the things that we would traditionally do. But obviously, using Gen AI is just one of these things to help kind of speed up document ingestion. That's obviously part of a POC, and there's a lot of things that we do to try and mitigate confabulations or hallucinations and things like that. So in a slightly different flavor of the very same, we could imagine that there's more than one organization, and these organizations are basically contributing and also looking to have their data checked against a blacklist or a whitelist or some other kind of probably even a risk scoring threshold or something like that. Um, and what we're seeing here is just, I mean, so I guess homomorphic encryption is one of those things that's probably, for certainly this crowd and the people that are in this audience are quite familiar with it. But just to mention here that we're using like an asymmetric system, so public key and private key. Obviously, the public key is used to encrypt the data, and the private key can be used to decrypt the result or indeed the actual data. And so what's effectively happening here was just similar to the previous slide, that the user will encrypt some attribute or other with the public key of the consumer. And then any sort of middle party or even the same party, but with some trust boundary, could then do the processing. So you can kind of outsource that process, and once it's encrypted, it's really just the case that the result that comes back from the encryption, the encrypted result, is only processable by the person who holds the private key. Okay, so there's a few different types of homomorphic encryption, and the main two sort of types are partial homomorphic encryption and fully homomorphic encryption. So I'll start off to discuss partial homomorphic encryption, which is basically a more simple version or an earlier generation of homomorphic encryption. So homomorphic encryption was presented originally in about 2009, and since then there's been quite a sort of significant uptick in the interest in the homomorphic encryption, and certainly the development of it and the performance of it, with things like noise cancellation, and the kind of bootstrapping process to help remove noise and allow bigger calculations to take place and sort of nested within longer running computations. When we think of the schemes that exhibit traditional homomorphic encryption properties, we can look at things like RSA and other things along an elliptic curves like El-Gamal. And so obviously in that case it's scalar multiplication and addition. But we also have things like Gold, Wasser, Macaulay, which would support XOR bitwise operations. So those sort of different algorithms sort of each have their own strengths, and in general are quite fast, and certainly faster than the sort of full-blown, fully homomorphic encryption. So just kind of sort of recapping as to what I was saying there, if we look at things like RSA, it works as for multiplication. Similarly with El-Gamal, and then we have kind of variants of El-Gamal here, and then we've got Palier, which is actually what the later homomorphic BG V and BFV are based on, which is what we've used for our POC and this party OpenFHE library, which is in C++ and Python. So you can see there that none of these homomorphic encryptions kind of do everything, right? And that's the point here, is that they all kind of do one thing, but they don't necessarily do everything. And so when we move on to fully homomorphic encryption, this is the kind of sort of heavyweight version, and it can do, multiplication, addition, subtraction, and also logic-based operations as well, which will happen, in terms of like the bitwise. So for example, things like XOR and NOT, different gates that could be used there for different types of logic. So if we look at how FHE's evolved, the original method by Gentry, like I said, was about it was 2009. And since then there's been development to push homomorphic encryption even further forward. And so in our POC, we're actually using a second generation encryption algorithm, and it is BFV. And it's very similar to BGV, which is another algorithm that sits and is considered a second generation. The third generation versions of the algorithm again, offer improvements over the earlier ones. It's probably not as sort of noticeable and profound, but certainly when it gets to fourth generation, it's a different ability in the sense that it can support floating point operations. So there is ways of supporting floating point numbers certainly in the other encryption schemes as well. It just involves additional logic, but natively CKKS supports floating points, and it's also a bootstrapped algorithm as well. And there'll be a slide that'll kind of just go over that, so I'll just hold on that thought. So if we just again look at a sort of bigger picture of how homomorphic encryption can enable sharing of data between disparate parties, or even just to pass through, maybe part of aggregate calculations and things like that. So if we take this example here, which is a patient who has some symptoms and has a particular kind of sort of set of symptoms that they have and a track record to match that. And we want to check and see if anyone else is having the same similar symptoms, for example, right? And maybe these are things that we expect to happen. They had the same 3-day run up, and then there was this same sort of event, right? Kind of trying to isolate things based on patient data. Now, the idea is sharing that patient data without massive, anonymization and things like that before it's just not possible. And so what we're kind of suggesting and what we do here is that the patient's data, which the recipient or the processor knows the formatting and stuff like that. If it's a spreadsheet, they know it's a set of weights and age and things like that. So they know what the structure of that actually is. And then what they can do is we locally encrypt it and pass that information to the provider who's looking to do the analysis on it. And obviously we're working on integer values, so we're not capturing names and things like that unless we've got a specific index set up to kind of convert those integers to some kind of other text meaning. And so what's effectively then happening here is we encrypt the data with the public key, pass it to the cloud. The cloud's going to do the processing on it, pardon me, and then there's an encrypted result produced from that. And that result can then be passed back to the hospital, and then the nominated person who is allowed to do the decryption, presumably the patient, is then able to get the result. And the interesting thing is here, during this kind of cloud process, this could be, 15 patients. So it could be we want to, work out the average weight of male and female patients, right? Something simple like that. And then we just collect all the data from all the people who are part of this test. And then we can sort of can verify that maybe we can calculate an average, for example, because we know how many people were involved, but we don't have to specifically, identify people in that kind of anonymous or pseudo-anonymous. Okay, so after sharing, so yeah, bootstrapping. So this is so basically with homomorphic encryption, one of the problems is this idea that noise increases exponentially. Effectively every calculation noise injection takes place, and if you multiply numbers, like if we took RSA for example, multiply numbers with noise, you're going to increase the noise and increase the noise, and so that was a limitation for homomorphic encryption, and one of the ways around it and the techniques that the newer algorithms use is a bootstrapping system. And so what this does is it basically resets the circuits back to kind of clean circuits again. And it does this periodically, adding some computational overhead, but removing this limitation where long running calculations will basically fail eventually because they just become too noisy and kind of overwhelm the main signal. So this here just sort of covers that bootstrapping and mentions these later algorithms which are the ones which basically have this as part of it. So uh, and again, just while talking about considerations, I mean it's kind of out slightly out of scope a little bit, but like any cryptographic algorithm or process, there's the potential for side analysis, side channel analysis, and something to be considered. And in this case, what we're showing is basically if you have access to a physical device, there's certain things that can give away telltale signs of whether this device is uh, whether you can track certain states of the processor, for example, and say, that we know these operations were taking place, and eventually over time, leaking key material or something, EM timing and power consumption all kind of fit in that same thing there. So it's a consideration, like it is for any other algorithm, I guess. Um, and some of the main homomorphic encryption libraries. Um, so I don't have experience of all of these, but certainly looked at Seal, Helib, and Palisade, which is actually what OpenFHE is based on, and which is what we've used and what we continue to kind of use now. But this here just shows, these are the open source contenders, and there is obviously some other really mature libraries out there. The Concrete ML library, for example, that Zama do is among the best. But these are kind of these open source libraries that we've got here. All right, so this is just sort of jumping into the over.
Hello, everyone. Maybe Jamie got disconnected. He'll be back shortly. Thank you.
Hi everyone. So very sorry about that. So my computer just turned off. It has power and it's plugged in. It's just I'm having a bit of technical issue with a physical problem. So apologies there. Hopefully didn't kind of derail things too much.
Yeah,
Um,
it's okay. Yeah, take it easy.
yeah, so I'll jump back in where we were. So I was kind of just talking then about sorry, the methodology. So let me just make sure I'm sharing my screen back out. Right. Okay. So yeah, so basically, this slide kind of kicks off into what the methodology is behind this, and I kind of talk about things like comparing, an artifact and seeing if we get an exact match and a zero, and but anybody who's worked in computer networking will know that it's probably much more useful to actually work in network ranges. And so we actually do work in network ranges in this prototype. It's just kind of abstracted as to how we do it. And so if we have an address, for example, which might be, if you just take a really traditional sort of normal address 192.168.1.1, and we say that that's a 24-bit subnet mask, then what we're really saying is that 24 bits of that IP address out of the 32 bits are associated with the network, and only 8 bits are associated with the host, which takes us to the 255 hosts minus the 255 for broadcast and 0. So what we would then do is we would normalize it before we encrypt it. So we know that the user is saying that this is a 24-bit subnet mask and this is the IP address that I'm looking for. It wouldn't matter if it was .1 or .15. We normalize it to 192.168.1.0, and that's actually what we're getting the exact match on. So homomorphically, we still are doing an exact match. It's just that we kind of pre-process the IP address first to normalize it so that we can find it within a range, because that's kind of typically more useful, especially because these IP addresses can rotate, and eventually IP addresses can be passed to a new provider who could be legitimate eventually, right? And so there's definite movement there. Things like telephone numbers are exactly the same, and VoIP service providers and stuff. So that kind of goes over that simple workflow. And so just kind of keeping an eye on things like time. And so looking now at the results, which is basically what kind of performance we've seen using these different algorithms, and sort of some simple testing and beginning testing around scale, and how that would how that'll impact, for things like the size of a blacklist and stuff. So if we first off look here, so I guess this thing here will be in your way. Yeah, so if we take a look at this table here, this is showing us these different algorithms, and then basically what the key generation time is, which is obviously a one-time thing, so it's not necessarily such a significant consideration. And then the encryption time that it takes to actually encrypt the data, and then the operational time that it takes to decrypt the data. And so the stats are pretty interesting, not surprising. Things like Goldwasser and Macaulay, being a partial homomorphic encryption, has this kind of sort of really impressive time here. Similarly with some of these other partial encryption algorithms as well. But if we look at BFV, which is what we use with OpenFHE, it's quite a noble, 16.4 milliseconds, which is certainly faster than some of these other partial algorithms, but not necessarily as fast as the fastest of the partial algorithms. But as I mentioned earlier, the bootstrapping, enabling, the noise cancelling for the calculations kind of cancels it out. Additionally, the functionality that you get from fully homomorphic encryption makes things like BFV a sort of more interesting prospect. And certainly when you look at the performance stats, it's not a massive difference for the benefits you get. And then this test here is basically running to see what happens if we have a blacklist of different size. So, for example, if the 800 IP addresses versus 50, and you can see quite clearly what's happening. I mean, it's just an exponential growth, right? It's doubling, and so this is without any parallel processes or anything. So there's a lot of different ways that you could effectively reduce that to be, buckets of 50, and multiply check multiple buckets at once in parallel, so you can kind of bring those speeds down. So this is more like a raw. This is how long it takes when we're just running it as a single threaded operation. So yeah, I think I'm kind of close to on time, so I'll just basically kick off with some conclusions. And so the conclusions here are that there is an increasing requirement for privacy-aware cybersecurity in general, and being able to process data while it's encrypted is a massive win. You can see these use cases across machine learning, sharing of statistics between banks, between healthcare providers, between shops, between any kind of retail, and anyone who wants to be able to share their information, but not necessarily make it aware that it was them that shared it, or they want to, check against some consolidated list without exposing a particular customer of theirs, or someone that they might later find it was not was not actually on the list in the first place anyway, so it was kind of an innocent IP, if you like. The paper outlines a method that requires a 32-bit plain text, so there's some adjustments to the modulus and the algorithm made for this, but otherwise, fairly standard. And so the summing it up is that the papers basically presents this method for using OpenFHE, and generating keys, encrypting the data, running various processing on the data, and then capturing the performance stats for that. So trying to kind of sort of test it in the real world, if you like. So that is basically the slide deck. I think they had a final slide that should say questions or thank you, but that's maybe somehow managed to remove it or delete it. But yeah, that's the presentation from me for the privacy aware blacklist and whitelist. Thank you.
That's